Our last topic for chapter 13 is looking at vibrations in polyatomic molecules, and specifically the idea of normal modes. So for polyatomic molecules, the first thing we need to think about is this idea of what we call degrees of freedom. So for each atom in a molecule, it can move in three different directions, 3 different degrees of freedom. It can go in X, Y, and Z. And so for each molecule, for a molecule, the total degrees of freedom are total DOF is equal to 3 times the number of atoms in the molecule. N equals number of atoms. Because they can all move with each other. Now, if all the atoms move in the same direction at the same time, that is just going to move the whole molecule in one particular direction. But if some are going one way and some another, that'll cause a rotation. And so these degrees of freedom combine to make different sorts of motions in the molecule. So we have a translational degrees of freedom, and there will always be 3 of those for a molecule, just like there are for each of the individual atoms, X, Y, and Z. We have rotational degrees of freedom, where the molecule will spin. So there are 2 rotational degrees of freedom if a molecule is linear. Otherwise, there are 3 for our 3 different A, B, and C axes that we talked about in the previous video. So this is for nonlinear molecules. And the reason we bring this up is because this idea of degrees of freedom will tell us how many vibrational degrees of freedom we have for a particular molecule. So it's just going to be whatever's left over. So 3n minus 6 for nonlinear molecules, or 3n minus 5 for linear molecules. And so this is subtracting off the rotational and translational degrees of freedom to tell us how many vibrations we're going to have left over. And so this will tell us how many different vibrational motions we'll have in a molecule. Now we can describe this, each of these vibrations. So each vibration we can approximate as a harmonic oscillator. And we get basically the same energy level expressions we did for a diatomic. There's more to it than that, but that's the simple version. And we can kind of treat our molecule as these vibrations as acting completely independent of each other. Of course, that breaks down, but that's sort of our starting point. And so we can use this to predict how many vibrations we'll have for particular molecules. My favorite example to always look at is water. So we have 3 times n. N is equal to 3, so we have 9 degrees of freedom. There are 3 translational, 3 rotational, since water is not linear. That means there are 3 vibrational degrees of freedom, and there are 3 different vibrations of water that we can observe. So there is, it doesn't tell you what these vibrations are going to be, but you can calculate this using computational chemistry. So one of the vibrations are going to be OH stretches. So we have the symmetric OH stretch and the asymmetric OH stretch. And then the final vibration we have is the bending mode of water. So and each of these has an associated vibrational constant that goes with it. And so this is true even for larger molecules, that we're going to see a specific number of vibrations, and each having its associated energy that goes with it. And we can treat it as a harmonic oscillator to a first approximation. And just like we did for diatomics, we can add in anharmonicity and calculate that as well. And so this is one of the very powerful things that computational chemistry can do, is allow us to figure out what these vibrations look like for molecules.